Hello darts fans, that's Timo Newman here, the transporter. Welcome to the good ship Undarted Waters. We are on episode 5 of this series, The Secrets of the Dartboard. There's actually one more to go, so even though it's posted as 5 videos, probably going to be 6, who knows, maybe even 7 if we discover more stuff in the next 24 hours. Anyway, just hitting some cool bullseyes and 25s there because the topic of today concerning the secrets of the dartboard is all about this wonderful region in the middle, the outer bull and the inner bull, the 25 and the bullseye. We've been concentrating so much on the segment and learned so much about the segment, but now we're going to get to the heart of the dartboard, the bull. So let me put my darts down, turn off this light and get my whiteboard. And you'll see I'm trying to be more efficient today because yesterday's video was very long. I apologize to everyone. That was me trying to keep it concise as well. So I apologize if that was overlong. I'm going to try and get today's video in a more sort of manageable size. Okay, so obviously this is a drawing of this, the outer bull worth 25 points and the inner bull worth 50 points, which also is the 21st double on the dartboard. As you know, you can finish a game of 501 on the bullseye. And if you've been following this series, you know that what we did in the first video was show all the measurements of the diameters of all the different circles on the dartboard, and from that we could calculate pretty much exact areas of anything we wanted to. The big single, the small single, the double, the treble of the segments, and we've got measurements here of the outer bull and the inner bull. So the 25 has got a diameter of on my dartboard of 32.5 millimeters, and the bullseye has a diameter on my dartboard of 13.5 millimeters. And that's all we need to do all these comparisons, because remember, we just say that the area of a circle is proportional to the diameter squared, and if we compare one circle to another, we don't need to know anything more than that to get the ratios. So let me just, without any further ado, start to show you some interesting results. So I better just introduce a little bit of notation. I'm going to sometimes write TF for 25, and if I write TF comma B, what I mean by that is the whole thing. So if I say the area of the 25, what I mean is the green area there, literally the area of the outer bull. But if I say the area of, see, TF comma B, or the area of 25 and bull, what I mean is this whole area, the green and the red added together. Okay, so the first thing I want to ask is, how big is this 25 and bull area compared to the whole dartboard, the whole scoring area of the dartboard? And we can work that out. So the area of the 25 and the bull together compared to the area of the dartboard, I'll just say board here. So what is that? I've got it written right in front of me here. That is 0.009. In other words, it's just a little bit under 1%. So this outer and inner bull together are just a little bit less than 1% of the area of the whole dartboard. And if you work it out exactly, like if Tony is throwing his random darts, then his chances of hitting the either the inner and the outer bulls is 1 in 109. So another way of saying this is that the scoring area of the dartboard is 109 times bigger than this little area, this little 25 bull circle. Okay, and the natural question to ask is, well, what about the bullseye? Okay, so the area of the bull compared to the whole board, what's that? It's 0.0016, and that's actually, if you work it out exactly, it's 1 in 633. So if you had a blindfold darts player just throwing darts at random at the dartboard for a long time, they'd be hitting the bullseye roughly on average 1 in every 633 attempts. So it's tiny, 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 the smallest target, of course, on the dartboard. So that just gives us a little bit of a sense of the relative sizes of these to the board. But where the meat comes in, where the really interesting stuff comes in with this topic is, let's compare the area of the 25 ring, so the outer bull, and the area of the bullseye. Let's compare those to the things we've been studying so much in the last few days, the segments. We'd like to compare these, say, to the double or the treble, or maybe even the single, and see what interesting things are lurking there. And we will find some very beautiful things, as we shall see right now. So let me erase these. So I think one way that I can do this is maybe to write a little table. And you'll remember that when we talked about the segment, what did we have? We had the whole single, so the big single and the small single. So I'll call that just the single. So this plus this, compared to the whole segment, remember, was 81.1% of the segment. We used that in yesterday's video, I think. And then the big part of that, so the big single, was 49% of the segment. So I'm just reminding you of these because we want to compare them now to the 25 ring and the bull, because that will be a really helpful comparison. The small single was 32.1%. So these are all numbers that we've seen before. And then we had the double and the treble. And these are really favorite numbers of mine. So the double was 11.8%. And the treble 7.1%. So this is all painfully familiar to us, very painfully if you actually had the stamina to watch the entire of yesterday's video. But the exciting thing is now we get to add in the outer bull. So I'm just going to call it the 25. So the outer bull and the bull, okay, the bullseye, the red dot. And you can see already from where I've put them in the order of things where they lie in here, right? Very, very nice this. So what we're now doing is comparing the area of the 25 ring to the area of a whole segment. So we're comparing this green ring to a whole slice of the pie, okay, a whole segment. And it's surprisingly big, 15.3%. Okay, significantly bigger than a double, which you probably knew, you could probably feel that, or maybe not, I don't know, it's not obvious by eye, but this is significantly bigger than a double, okay? And then the bullseye comes in at 3.2%. So less than half the size of a treble, very wee, as we say here in Scotland, okay? So that's quite helpful in seeing where the outer bull and the inner bull lie in this kind of hierarchy of the size of things, and the segment, so this shape is a very useful kind of like your yardstick on the dartboard. The area of that's a good yardstick for measuring the other areas compared to that, rather than measuring everything compared to the size of the whole board, because that's kind of too big and it doesn't really give you much intuition. But this, I think, can give you a lot of intuition. So we can just look at this and say, right, so the 25 ring is a fair amount bigger than the double. It's less than half of a small single. So a small single we know is a tricky target. So the outer bull is less than half of that. Okay, so that's kind of interesting. And we can read off lots of more things from there. So what I'm going to do now is erase this table and just point out some of the really interesting ratios. Okay, so sorry to keep erasing interesting stuff. I guess you can always pause the video if you want to just kind of study it more, or write down the numbers and do your own kind of thinking about it if you like, So let's just write down some of these ratios then. So the area of the 25 to a double, and I'm just going to use shorthand notation here. We know what we mean. The area of the 25 compared to a double turns out to be roughly 1.3. So in other words, the 25 ring is about 30% bigger than a double. Okay. And compared to a treble, and this is a very interesting number, as we'll see shortly, turns out to be about 2.2 times bigger. So the 25 ring is more than twice as big as a treble. Okay. Now what about the size of the 25 to a bullseye? So what's the size of the green area compared to the red area? And this is not to scale. I just used a syrup tin and a plate. So this is definitely not to scale. But what's the ratio of the area of the green outer bull to the bull? That is an interesting number, 4.8. So we're going to return to that number in a minute to talk a bit about that a bit more. And what's the ratio of the treble to the bull? That is about 2.2. So I want to draw your attention to this. And we'll mention it, we'll go back to this in a minute and talk about it a little bit more, but let's just notice that the area of the outer bull compared to a treble, that ratio is the same as the area of that very same treble to the inner bull. That's a very beautiful thing, a very beautiful thing. And that we have a name for that in mathematics, that kind of feature, and it will be very familiar to you intuitively, and we'll get to that in very shortly. Okay, but we definitely noticed that is quite a cool thing. We also noticed that the 25 ring is about 5 times bigger than the bullseye in area. And you wouldn't necessarily think that when you look at the dartboard, but this is why we do this geometry, because we can't trust our eyes. I've spoken about this before. The characterization of reality that we carry in our brains through our eyesight, although extremely useful and necessary, of course, for us as dart players and as living human beings, is not an accurate representation. And our eyes, isn't there that phrase, your eyes are playing tricks on you? Well, they do that all the time. So thank goodness we have some basic geometry. And what's cool is all the geometry, all the numbers we get, everything comes from a ruler. We just measured diameters of circles. We get everything from that. And that's really beautiful. Nothing fancy, no fancy formulas. We just say the area of a circle is proportional to its diameter squared. And the difference in area between two circles of a ring is just the big circle minus the small circle. That's all we've been doing. This whole series is just using that. We get so much from that. So these are interesting numbers. And what I want to do then for the rest of this video is just focus in on this one. And I want to focus in on this one, because I just think that they're very cool and kind of helpful to us as dart players. So this might be the final erasing, I think. Okay. So let's start with the with what we found there about the, what did we say? The area of the 25 compared to the area of the bull was about 4.8. So what we can do is actually rephrase that slightly differently. Let me write it like this, that the area of the bullseye divided by the area of the 25 and bull combined. So I'm adding these two areas to get the area of this whole object and comparing that to the bull. When you work that out, is 0.17 roughly. In other words, and this is the really important number now, 1 in 6. So I think I mentioned this when I was doing that video on the Matthew Edgar challenge number 6, the first kind of really difficult one where you have to get 10 bullseyes, and your score stays alive if at least one dart in your visit hits the outer bull. And I mentioned there, I think, this particular fact here, that if you throw darts, sort of, let's say we program Tony to throw darts at random into the bull area, so all his darts landed in this bull area, 1 in 6 of his darts would hit the red inner bull, and 5 out of 6 darts would hit the green outer bull. And when you train up with that Matthew Edgar level 6 challenge, it becomes relatively comfortable hitting this whole target here. So you can fairly reliably hit that. And so when you have outshots where you have, say, you want to get a 25, so like the outshot for 61, the traditional way is to get outer bull double 18, 25 and then 36 makes 61. And you'll often see players go for that, okay, because they know that as long as they don't aim too much at the bull, if they just aim in that central area, they're pretty confident of hitting it, and they've got a 5 out of 6 chance of getting the outer bull, so it's a pretty safe bet. And then they can go for their double 18. Now sometimes they get the bull and they smile because they know they've been unlucky, because that 1 in 6, if you hit the inner bull, on that outshot you're then left with 11 and you have to go 3 double 4 and you only get 1 dart for the double. So the commentators often tisk that route because they say, oh, the danger is you hit the bull. But it's a pretty safe way to go, because statistically you've only got a 1 in 6 chance of hitting the bull if you're not really aiming for the bull, but you're just kind of throwing a dart at that central area. And like I say, with a lot of practice, you can be very kind of comfortable hitting that area, like I did at the start of this video. That was just my first try, and because of having been a sufferer of that a year ago, that particular level, I feel very comfortable hitting the bull because I spent 2 months doing nothing else than aiming for it. Okay, so this I think is one of these nuggets I've talked about in this series, a good thing to bear in mind. Okay, yeah, the red inner bull is 1/6 the area of the whole circle. It's 1/5 of the area of the green ring. And the green ring plus the inner bull add up to 6 pieces of that hole there. Okay, so 1 in 6 is the red and 5 of 6 is the green ring. Okay, so that's one very interesting thing. And then the second interesting thing, let me just erase this and make more space, is comparing the inner bull and the outer bull to a treble. So let me try to draw a treble here that's kind of hanging around, lurking. So there's a treble lurking over here. There's the, that's treble 4, kind of lurking around, hanging, waiting for someone to hit treble 4. Can you imagine being treble 4 on a dartboard? We talk about having no job. Like no one aims for treble 4. I always feel sorry for those low trebles, because so any treble below 7, no one aims for them, because you'd never go for treble 1 to get 3 or treble 2 to get 6. You just go for the big single. So they only get hit by accident. I just feel like, I know that they're not real people or have real like spirit, but I still feel sorry for them, because it's just like they're there, they turn up every day on the dartboard. They're never late, they're conscientious, but they're just always overlooked. And when they do get hit, the dart player always like curses because it's a mistake. They were going for the treble 18 and they hit the treble 4. So whenever you get employed, you're just cursed. What horrible existence. So we're honoring treble 4 here on this video. We believe in you, treble 4, for the purposes of this comparison. Okay. So what we found that the area of, what did I say? The area of a 25 compared to the area of a treble was about 2.2, and we also found that that same number, 2.2, was the area of a treble compared to the area of a bullseye. So that's really interesting. And what this means is, I don't want to do maths on this show, but if you just excuse me doing this, if I multiply this up to here and this up to here, what it says is that the area of a treble squared, so multiplied by itself, so area of treble times area of treble, is area of 25 times area of the bullseye. And this is, you know, for a physicist, we love beauty. You see, physics of the universe is kind of studying beauty, and many of the equations of physics are very, very beautiful. Okay, and people talk about the unreasonable effectiveness of mathematics to describe the universe. Like, why does the universe allow itself to be described so beautifully by mathematics? But it really does. Okay, and I think the dartboard allows itself to be beautifully described by a maths equation. The area of the treble squared, so the area of a treble times itself is the same as the area of an inner bull times the area of the outer bull. That's kind of amazing to me, you know. Now, if you are a mathematician, what you're itching to do is take the square root of this formula. So if you take the square root of this, what it means is that we, instead of squaring this by itself, we take the square root of the other side. So another way of saying this is that the area of a treble is the square root of the area of a 25 times the area of the bull. Now, all of that lingo isn't important, but we do have a name for this. That's why I wanted to just write that down. This has a beautiful name. This is called the geometric mean, or the geometric average, which is quite fitting that this, because this is a series on geometry. So the geometric average. Because when we think about average of two numbers, what we normally think is, oh, I add one number to another and then divide by 2. That's true, that's called an arithmetic average. But another way of taking an average is that you take one number and you multiply it by another, and then you take the square root, and that's called a geometric average. And it turns out that the treble is the geometric average of the inner bull and the outer bull, and that's just a beautiful thing that we should just enjoy the beauty of it. Okay. You might say, well, who cares about that? What does this all mean? But just to give you a sense of this, like, you know, who would ever use this geometric average? Think about it like this. Like, if you have a photograph on your computer screen, and then you might have like a feature on your software that you can make it bigger, right? So maybe there's a feature that says you can multiply it by, make it 1.5 times bigger. And so you do that, okay? But there might be another feature that says, oh, you can make it 1.5 times smaller, right? And then it would look, you know, something like that, right? Would be, and it's all the same photograph, but you've made this one 1.5 times bigger, then you've made this one 1.5 times bigger. But you see, this is where the geometric average is. The area of this one is the area of this one times this one and then square root. So this is the geometric average of these other two. So if you have like a scale factor and you blow something up and then you blow it up again, the middle one is the geometric mean of the smaller one, the smallest one and the biggest one. So it's like someone took the bull, expanded it by 2.2 and said, let's call that a treble, and they made it into the shape of a treble. And then they took that treble, they expanded that by a factor of 2.2 and said, let's make that a ring. And by magic, it fit beautifully around the inner bull, and they said, right, there's our dartboard. Oh, and we need doubles. Let's use that beautiful number 5/3 to make the doubles. I mean, there's all that beauty hidden inside. Isn't that gorgeous? So I couldn't resist telling you about this geometric average, or geometric mean, as the mathematicians call it. So I think that's everything I've got to say today about the bullseye. Hopefully a shorter video today, but I do tend to witter on, and friends and family of mine are used to this. So I don't want to stretch the patience of my loyal viewers. I get so many nice comments through YouTube that I always try to answer, which is really helpful. So please, if you have suggestions, if you have ideas for future videos, if you have corrections, I'm open to all of that. Okay, so thank you ever so much to everyone that takes the time to watch these and to provide that feedback, because it kind of makes this channel more of a community for dart players that are interested in what's underneath the game. So not just the results of the tournaments and stuff, but what's actually underneath the game and how science and maths can tell us more about that. So with that, we're going to have one more video on this topic tomorrow, which is going to be all about what does Tony hit if he has the whole dartboard to aim for. So what kind of score does a blindfold player get at darts? And the answer is going to be a bit depressing for us dart players. So with that, I'll say goodbye. 3 darts at the oche, make them count. Thanks very much, and I'll see you next time.